Okay, so we are doing convex mirrors. So you mark the centers of curvature, one in front, the other in the back. That's the actual center of curvature. Then we mark the focal points as well. That should be the F prime, better label it F prime. And we put an object at distance P from the mirror. In the next, okay, so this light ray, right? So that's what we have initially, right? First light ray parallel to the principal axis is going to diverge, but this diverging light ray is going to pass through the focal point. If you extend it, if you extend the back of the arrow, it's going to pass through the focal point. Then we have this other light ray that's going towards the focal point. Is going to reflect parallel to the axis. That's all we need to find out the image, nothing else. But if you want, right, you can get the third light ray, 3 different light rays. Parallel to the axis, towards the focal point, and the third one towards the center of curvature. Because this light ray that goes towards the center of curvature reflects on itself, right? We don't have to do anything else unless we want to, format shape, put a second arrow here, just to emphasize the fact that the light ray is reflecting on itself. Okay, and now the intersection of all those 3 light rays results in a image that, by the way, is behind the mirror. So that's all you have to know. There's no other case that you have to worry about, okay? That's the distance of the image. And by the way, we got put that I here and P here, according to the notation of the book. Do we have, yeah, I gotta correct that here as well. P, P. Anything else? Man, so many that I missed it, right? Here you go, one more. P, P, P. Okay, now you got it, P, P. And that's going to be the distance of the image. Let's move a little bit to the right, huh? Make it look better, right? And that's all you have. There's no other situation. You can position this image, this object anywhere. And if you go to the simulation, I posted the address of the simulation in my notes. Here you go, right in here. Okay, and here you go, the object. In this case, they put the object on the right side of the mirror. That's the front of the mirror, that's the back of the mirror, right? If you want to make it, if you want to play with concave mirrors, you gotta switch the position of the object. Here's the concave mirror, on the other side is the convex mirror. And let's take a look. It doesn't matter where you position the object. The image will always be behind the mirror, and it's going to be smaller than the object. Okay. Here you go. Height of the object, height of the image. Okay. So, and the image is always going to be upright and virtual. Okay, so okay, so here we go. Concave mirrors have real upright images. No, real upside down, right? Upside, real inverted images, and virtual upright have real inverted and virtual upright images. Convex mirrors have what? Only virtual upright images. Assuming that the object, and that's assuming that the object is real, okay? And because there are virtual objects, okay? It's possible to have virtual object. We're not going to cover it at least now. Assuming that the object is real. We have the following image. We have the following images. Okay, concave mirrors have real inverted and virtual upright images. Convex mirror has only virtual upright images. And we can come up with a simple, right, example. Let's get the formula for, let's see, I guess I can do it in a better way. Instead of, here you go. This is the formula here. Let's do, this mirror also obeys this equation. Equation for both mirrors, right? Equations, and I'm going to put equations. And we have that other equation too, right? That we looked at. That we go, that's the magnification equation. Like that. No, so let's see. Example, right? Question here, is magnification a vector? No, magnification is not a vector. It's a scalar. Okay. So this is a scalar, this is a scalar. Okay, example, a convex mirror of focal distance f has an object located at P greater than F. Okay. Find the image, find the position of the image. Solution. Okay, so it's gonna be like that. F. There is one little trick here, okay? There's one little trick that I didn't tell you. Okay. For convex mirrors, F is greater than 0. For concave mirrors, F is greater than 0. For convex mirrors, F is less than 0. Okay? So you gotta put here, minus F. So here's the focal distance minus F. Here's the position of the object. That's going to be positive. And what we have. So if you're getting the wrong result, right? Most likely that you're not using the right signs, right? Right from the bat, from this equation here, I know that there is a problem with the sign, right? If I was not using the sign here, right from this equation, I know that there's a problem with the sign, right? This part cancels this one, which means the image is formed at infinite. That's not that doesn't happen for convex mirrors. Okay, so you must have a negative sign in there. We pass to the other side. That's going to be equal. Okay. Minus 2 over F. And the image that is formed is going to be I minus F over 2. One more student coming. The negative means that the image is virtual. Let's take a look at the simulation. I'm going to put the position of the object equal to this one. Okay. So the position of the image is a half the focal point, focal distance. Okay. And the image is going to be smaller. Now look at a convex mirror focal distance minus F has an object located at P greater than I. Find the position and the magnification of the image. If you repeat what the negative will do to the image. Okay. Yeah, so well, the first thing that you have to know, right, Raymond, that you have what you have to know. You gotta make sure that you are using the proper sign for the focal distance of the convex mirror. Okay. So if you miss that, right? If you miss that and try to solve the problem in the incorrect way, right? If you try to solve the problem in the incorrect way, you're going to see that you're going to get an image that's formed. This term here is going to cancel out this term, right? And you're going to get a solution that the image is going to form at the infinite, okay? Which is not correct, okay? That's and that would give you a hint that there is something wrong with the setup of your equation. But what you have to remember is those two items here. Convex mirrors, F greater than 0. Concave mirrors, F greater than 0. Convex mirror, F less than 0. Okay, that's the point that you have to remember. Okay, we can do for other things, right? Let's say magnification. Go, magnification. Let's calculate the magnification now, right? magnification minus I over P. I is minus F over 2. Minus F over 2. P is F. Right? So here you go. F cancels out with F. Negative cancel with negative. 2 goes downstairs. And we finally get half. That's the magnification. I'm going to emphasize the fact that it's a positive number. Positive means upright. Positive sign in the magnification means upright image. And the image is smaller than the object. Let's see if we can get something more general than that, right? Okay, so let's see. And let's see if there is any other situation for, let's prove mathematically that there's no other situation, right? For a convex mirror of focal distance has an object located at P equal to AF, okay? Where A is a real number. Find the position magnification of the image, right? I'm writing down the position of the object in terms of the focal distance. The A can be either a number less than 1 or greater than 1. It's a real number, okay, greater than 0. I'm looking greater than 0. Okay, so here you go. Let's play a little bit. P has an object where here you go, where P is greater than 0. Let's put it this way. Emphasize the fact that's greater than 0. Greater than 0. Where A is a real number. Is a number also greater than 0. Greater than 0. Find the position magnification of the object. Right? So let's play a little bit with this equation, see if we can find a generic solution for the image. That's the equation that you want to play with, that you want to work with. This term is going to be minus here. Here we're going to have an equality. Okay, and what else we have? We're going to put everything under the same denominator. Right, let's see. Put everything under the same denominator here. And now that we put everything under the same denominator, and I can put a negative right here. Okay, this negative goes here. Let me see if I did it right. Oh yeah. Okay, the way you do it like that. That's how the way you do it. Right? You have a negative here, you have a negative here. So I'm putting the negative in evidence. So we end up having this solution. I is equal to AF, A plus 1, A plus 1, right? AF, A plus 1. F is positive, A is positive. This is positive according to this equation, I is always less than 0. Always. I is always negative. I is always negative. No matter what is the value of F and A. Okay? No matter what the value of F and A. Furthermore, well, that's why that's what you wanna leave here. It's always negative. So the image is always negative, no matter the values of A and F, right? No matter the values of A and F. Now let's take a look at the magnification equation for the magnification here. So this is a proof, right, that you're going to have only one type of image forming. Now let's do this one here. This one is like that. I is like that. P is AF, where A is a positive number. It can be a positive number anywhere between 0 and infinity. Okay. So we're going to I'm going to cancel out this sign, positive. And we place the A plus 1 downstairs. Like that. We write down AF here. Look that my sign is positive, means that the image is upright. And I'm going to cancel out AF. This AF. Okay, A plus 1. A is positive. Consequently, this number here is always less than 1. So you have 1 being divided by a number that's greater than 1. That's always greater than 1. So here you go. We proved that for any at any position of the object, comma, the image of the object will always be virtual. Virtual means I less than 0 and upright. Virtual and upright. Oh, not just upright, virtual, upright, and smaller, right? And smaller than the object. So the virtual image is here, right? Let's see, according to this equation, I is always negative. So the image is always virtual, not negative, but virtual. That's what negative means. And because M, right? The thing is gonna always be less than 1, greater than 0. 0, like that. And we prove that whatever the object is located, whatever the object is located, in front of the mirror, the image of the object, provided, of course, provided p greater than 0. There is a case in which p can be less than 0, okay, but we're not going to cover that. The image of an object will always be virtual, upright, and smaller than that of the object. That's the condition here. A32, go, wherever the object is located in front of the mirror. Okay. So for, one more important thing, for mirrors, virtual images are always located behind the mirror. Okay. I'm pointing that out because the opposite is true for lenses. The opposite is true for lenses. And that's what we are going to do now. We're going to look at lenses now. The techniques that we use for mirrors are very similar to the techniques that we use for lenses as well. Okay, we already covered that part here, right? One important thing that I want to mention right now that I didn't mention before, I did mention, but I didn't illustrate it, right? Is that when you get total internal reflection and the device has this geometry, right? With air below and air above, you can have light propagation over very long distances because you have very little loss due to the light that is initially leaking out. Okay, and that's the type of that's what we call total internal reflection, right? And that's the type of phenomenon that is exploited by optical fibers. Here you go, right in here. Yes, that's right. Total internal reflection occurs only when this medium here has a refractive index higher than the external medium. That's right. You cannot have total internal reflection if this medium here is air and the outside medium here is, for instance, water. Yeah, you do not have total internal reflection. Then you don't have total internal reflection, okay? There will always be light leaking out, right? If you have the situation inverted, right? I can even illustrate that for you. So let's say instead of glass, we have water here, right? Water, no, air. Refractive index 1.0, and we have water here, refractive index 1.33. What's going to happen? That you cannot have total internal reflection under this condition, right? Because the light will always move towards the normal, right? So here you go. Because of the higher refractive index, the light will always move towards the normal, and you have a leakage of light, whether it's above or at the top. And here you go, 1.33. Second medium is a higher refractive index surrounding the medium of lower refractive index. Do not accommodate total internal reflection, ITR we call it. TIR, not ITR, TIR, total internal reflection, TIR. Like that. And then this one here, go down, right? So here we go. also because the angle of incidence is always greater than the angle of reflection. Let's see, it's also because the angle of incidence is always greater than the angle of reflection according to Snell. No, it's not because of that. That's because the refractive index here is larger than the refractive index there. Okay, that's because that every time that you go from a medium of lower refractive index to higher refractive index, the light is redirected towards the normal. Okay, no matter what is the angle, that no matter what's the angle of incidence. Okay, you can have an angle of incidence that's very close to parallel, and the light is still gonna it's still gonna refract towards the normal. Okay, that's the reason. That's the reason. So total internal reflection can only happen if you have, that's the reason that total internal reflection can only happen if you have a higher refractive index here and a lower refractive index here. Okay, that's why. So then, well, now let's talk about the lenses, right? Spherical lenses, just like mirrors. Spherical lenses are formed out of a sphere. Here I have a plane convex lens. This surface here has a radius of curvature r, and this surface here has a radius of curvature in infinity. I'm gonna put it in a different color here. Okay, the radius of curvature of this surface here is going to be very large. Okay, and so it doesn't have any curvature at all. The larger the curvature, the flatter the surface, right? The larger the curvature, the flatter the surface. And I'm even gonna put here is a red color to emphasize the fact that this arrow is for the other surface. Like that. So there are all sorts of spherical lenses. You have planar convex, you have biconvex, right? That's a positive lens. We call that a positive lens. A positive mirror is concave. A positive lens is convex. See the difference? Go all the way, and the inverse, right? So now let's talk about mirrors. And now let us talk about lenses, right? Positive mirrors are concave. However, positive lenses, okay, and by positive I mean converging. Positive converging lenses are convex, and vice versa. And then you can have the other negative diverging mirrors are convex. However, negative. Negative diverging lenses are concave. Let us start with positive lenses. Positive lenses. You can have a plane convex lens, plane convex, biconvex, and you can also have a combination of convex and concave lens, provided the radius of curvature of the convex surface is smaller then the radius of curvature of the other surface. Okay, we can have so fraction. Let's see if I can. I have only a planar convex lens here. Let's see if I can draw it for you. Okay, so here, see, okay, here you go. So what I'm gonna do, I'm gonna try to do here. It's gonna be kind of difficult. Let's see. I'll have to do from scratch, and I'm gonna need grid lines. Okay. What I have here is not what I want, so let me take it out. I'll keep those for now. Okay. No, that's not what I want. I want another one. This one. See, we have those features here in PowerPoint that allows you to draw sections of a circle. Here you go. Section. This is a section of a circle. And okay. That's a very, that's a very small curvature. It's very small radius of curvature. So let me make it a little bit larger. I want to make sure that I end up with a okay, here you go. Yeah, that's one surface. That can be one surface of the lens. And now I can come up with the surface, with the other surface of the lens. Okay, so 1, 1, 2, 3. I want to remember. I want to have a section of a circle here, right? So it looks like I have a section of a circle. Let's see. Let me get a little bit larger so I can have a better reference here. 1, 2, 3, 4. Right, 1, 2, 3, 4, right in here. And I want to do the good. Okay, and now this is a biconvex lens. What you have here is a biconvex lens, okay? Let's touch it, and then I can shorten. This is a positive lens. Make it look nicer with I don't like this this light blue color. That unfortunately is standard for okay, biconvex lens. Like that. But like I said, we can have a convex concave lens. I see that's one surface. And I'm going to use this other surface. But instead of using this side, don't forget this one has a larger radius of curvature. Do I get it? Yep. Now I'm gonna fit the surface right here. This is still a positive lens because the radius of curvature of the concave side is greater than the radius of curvature of the convex side. Okay, positive lens, positive lens. This one has a radius of curvature. See here, I'm going to emphasize. Okay, so this radius of curvature here is going to be somewhere around here, right? Around here, somewhere around here. It's not exactly, but that's good enough. Two squares of the radius of curvature is 2 squares, whereas this one, the radius of curvature is just 1 square. Oops, nope. Okay, the radius of curvature of the other one is just 1 unit. Right in here. Okay, this is still gonna be R prime, this one. This is still gonna be a positive lens. And then we have that planar convex lens that I want to, oh, not here. Not this one. Yeah. Ooh, not good. I gotta figure out a way to. Okay, so yeah, okay. Now I'm gonna get it. Yeah, but then I'm gonna hide the other ones. Okay, you go. Or even better, I'm gonna send that to the bottom. Send to back. Yeah, now we got it. Okay, so they are all positive lenses. Lenses. Positive lenses converge light. We get this guy right in here. Okay, and refracting surfaces. Okay, there is one equation. You know what? I'm going to skip the. I'm just gonna do sing lenses, okay? Sing lenses. Okay, so For the case of thin lenses, we're doing only thin lenses. Thin lenses. And then we have negative thin lenses. Plane concave, biconcave, convex concave, provided the radius of curvature of the concave surface is less. No, it's a concave surface is smaller, is less than the radius of curvature of the other surface. Okay. So two types of lens we are sticking. Let's talk about positive thin lenses first, right? Well, we have a similar equation for the position of object for a thin lens. If the lens is not seen, this equation doesn't apply anymore. You need a correction, okay? Thin lenses equation. The inverse of the focal distance is equal to the inverse of the position of the object plus the inverse of the position of the image. There is another important relation that mirrors do not have. Important relation for the focal lengths of the lens. And this relation is like that. The inverse of the focal distance is going to be a function of the radius of curvature of the two surfaces times the index of refraction. I'm not going to prove that. Okay. n-1, but then n-1. The focal distance goes with the refractive index. The higher the refractive index, right? The smaller, let's see, the higher the refractive index, the greater this ratio. The greater this ratio and the smaller the focal length is. So note C that the focal length decreases, right? Decreases with the refractive index. The higher, in other words, the higher the refractive index, the stronger the converging power of the lens. So the focal distance must decrease, right? Focal distance must decrease. And by the way, this equation is good also. Thin lens equation. This equation is valid only for thin lenses surrounded by air. Okay. Let us play a little bit with this equation here. Let us play. I'm going to put that in Excel. And, find the focal distance of a planar convex lens with the convex surface, with the convex surface having a radius of curvature of 1 meter. Okay. example. So we have two surfaces here. Okay, by the way, I gotta tell you something else too. R1 in the above equation, R1 is the surface nearer the object, radius of curvature of the surface nearer the object. Okay. So of a radius, find the focal distance of planar convex lens. The material is glass. Material is glass with n equal 1.5. Okay. Solution. So that would be something like here you go. Let's say an object is right in here, right? Let's say we have an object. Let's see if I can. We have an object that is facing the planar surface. So that should be R1. Okay. So what we're going to do here is the following. R1 is going to be a large number, a very large number. I'm going to put that here, infinite. This is going to be, oops. And this is going to be 1.5. Yeah, R1 is infinity because it's the planar surface. Yeah, it's a planar surface. Going back to the drawing here, right? Okay, so the radius of curvature of this planar surface is infinity. Okay. The larger the radius of curvature, the flatter the surface, right? That's how you should look at that. Just like I illustrated right in here. Okay. The larger the radius of curvature, the flatter the surface, right? If I increase even further, this thing is going to become even flatter and flatter. When the radius of curvature is infinity, it means that the surface is going to be a planar surface. Okay. Make sense now? Yeah. Well, just make the limiting condition, right? Here is a surface with 1 unit of radius of curvature. It's very protruding, right? The curvature is very intense here, right? And here is the curvature of another surface with 2 units, right? You make a surface with 3 units, it's going to be, it's going to be flatter than that one, right? 4 units, even flatter. Then you do the limiting condition. For a very large number, the surface is going to become a planar surface. Okay, that's how you look at that. Just think about the limiting condition. Think about the surface here. If the radius of curvature is 1,000 of those squares, it's not even gonna fit here the radius, right? But that's how it goes. And I'm getting here 1 meter, right? And this term here goes to 0. This term here is 0.5. And we're gonna get 0.5 divided by 1 meter. Okay, and then I end up, according to this equation, I end up with a focal distance equal to the inverse, right? Inverse of half would be 2 meters. Well, it is only supposed to be a positive, okay? Because it's a so what the book says that this R1 here is the surface closer to the object. That's not you know, there might be a mistake there in the book. See here, R1 is the radius of curvature of the lens surface near the object. Yeah, that's not a good definition here, because we're not getting the right results. Okay. So it should be, you know, all the way around. That should be, you know, infinity here. Okay, so that's what we end up getting. Should be, let's see, I'm gonna put it all the way around here, plus. And what if the refractive index increases to 2? Then you're going to have 1 here upstairs. Let's see. If you have 2 here, refractive index 2, we're going to have 2 upstairs, and the focal distance is going to be 1 meter. Okay, just like I mentioned before, the higher refractive index, the stronger the converging power of the lens. So that's that's the equation of the lens maker equation. We call it the lens maker equation. Okay, it's 9:05. Let me take attendance here right now. And yeah. Is the planar lens is just an approximation of a very large lens. It's the approximation of a of a surface with a very large radius of curvature. Okay, is the point here is the radius of curvature. It does not necessarily mean that's the large lens. Okay. Okay, not so no, makes sense, right? Is a lens with a very large radius of curvature, not necessarily a large lens. You can have a large lens that has a very small radius of curvature. Okay, and let's go to our. I'm gonna take attendance right now, and Amy, are you there? I see Amy here in my list. Amy, are you there? No? Okay, I'm gonna put a star on Amy's name. And Andy? Hello, Andy, are you there? Yeah, I cannot hear you, Andy, if you can. And I cannot hear you, Amy, either. If you may please type there your message there in the chat box, okay? So, Alex Hernandez. Thank you, Alex. Sartak. Thank you. Zaid. I see Zaid here. Okay, thank you, Zaid. Alisa.
Here.
Thank you. Kartika. Kartika. That's here. I see Kartika here, but I don't hear. Okay, let's put a star. Next is Mary.
Here.
Thank you. Raymond. Raymond is here, right?
Hello.
Thank you. Ashley Tai.
Here.
Thank you, Ashley. Alexis Valley. Alexis, I see Alexis here in my list. Hi, Alexis. Are you in front of your computer? Okay, I'm gonna put a star here. Jeshwan.
I'm here, Professor.
Thank you. Basilio.
I'm here.
Thank you. Now let's see, Daniela. Is Daniela here? I don't see Daniela. And Sydney.
I'm here, Professor.
Thank you. And Sumana. Okay, thank you. So let's see, we have 11. Let's see. Okay, Amy, are you there, Amy? Let me give another opportunity for you who didn't answer. My roll call. Amy, Andy. Okay, Kartika. And Alexis. Okay, so let's have our break now and break from 9:10 to 9:25 a.m. Okay, so see you in 15 minutes. Okay, so now let's start looking at the formation of images by the lens, right? That's the most important part of this chapter. And okay, so here we go. We have this planar convex lens, and the way we form images, just almost the same way we do images with mirrors. We come up with the axis, the principal axis, right? And but before we go to actually image formation, I'm going to give you a qualitative idea of how light refracts through the lens, okay? So if we have a light ray that's incident, that's parallel to the axis of the lens, to the main axis of the lens, it's not going to refract through the first surface, okay? And then when it reaches the other surface, what's going to happen? You have to come up with the plane that is tangent to that surface of the lens. After coming up with this plane, you're going to draw the normal to the surface, so you can find out in which direction the light ray is going to be refracted, right? That's why we're doing that. And here is the through ray with no refraction. That propagates with no refraction whatsoever. But because you're going from one medium of higher refractive index to a medium of lower refractive index, the light ray is going to move away from the normal. Move away from the goes through. Let's call it the goes through light ray. It's a very good concept. I'm gonna write that down here for you, so you can go through light ray. Goes through light ray. That's the one. Those goes through light ray, they're there just for reference purposes, okay? They don't exist at all. They don't, light rays don't go through the lens without any refraction, but they're there just for reference purposes. So the point where the light ray crosses the axis is going to be your focal point, okay? And then for the case in which you have a parallel light ray, right? That for the case in which you have a parallel light ray parallel to the axis. Okay, this is the representation of the lens, a simple representation, so you don't have to keep on doing fancy drawings. That's representation of a positive lens, converging lens. Here's the axis of the lens, principal axis, focal point. You gotta draw another one in front, the other behind the lens. Whether it's in front or behind, it depends where the object is located, okay? Here you go, here's the object. And now we're going to draw our first light ray. The light rays that are parallel to the main axis are going to converge, refract towards the focal point. The second light ray passing through the point F prime. That's the mirror image of F. And what happens to those light rays? Because they are refracted parallel to the axis. And that's where my image is formed. You can have a third light ray too if you want. The third light ray that passes through the center of the lens doesn't suffer any refraction. Okay, 3 different light rays for the lens. Okay, so let's write that down. We have everything documented. How to form images with a lens. One, draw the lens, right? Draw the axis of the lens. Locate the focal point. No, locate, draw the focal point, right? Draw the focal point F along the axis and its mirror image F prime. Draw the focal point F behind the lens and along the axis. And its mirror image F prime in front of the lens, right? Draw the object wherever it is located. first light ray can be the one parallel to the axis. Refracts towards the focal point F, right? Second light ray passes through F prime and refracts parallel to the axis of the lens. Oh, let's say third light ray, right? You don't need a third light ray, but if you just want to make sure that you're doing everything right, third light ray passes through the center of the lens unrefracted. There is no center of curvature here, right? Just like in the mirror, in the mirrors, we do have a point that corresponds to the center of curvature. In the lens, we do not use the center of curvature because the lens has two centers of curvature, right? Which one are you going to choose? So those are the three light rays that we choose. Okay, intersection of these three light rays, is the location where the tip of the image is formed. Going back. Okay, so here you go. That's the location of the tip of the image is formed. Okay. Let's do that again. Here you go. Let's play the movie again, right? Lens. Axis, principal axis of the lens. Focal point F. Mirror image of the focal point F prime. Object anywhere, past the focal point, the image of the focal point, right? Light ray parallel refracts towards the focal point behind the lens. Light ray passing through F prime is refracted parallel to the axis. At this point, you already can draw an image of the position of the image, right? But then if you want to add the third light ray that goes through the center of the lens, you can do that too. Okay, this is the distance P according to the book. This is the distance I according to the book. Okay. P. Let's use a capital I here. Capital I here to distinguish from the other I. P. Lowercase I. Focal distance, right? That's the focal distance. Uppercase I. What we have here, you go. And now, that's for the position of the object behind F prime. The image that's formed is going to be further away from F. What happens if the object is exactly F prime, right? We form an improper image, just like we got that for the mirror. We draw the light ray parallel to the axis, it converges towards F. Then we draw the light ray incident at the center of the lens. Notice that those two light rays are parallel to one another, right? And we can even prove that mathematically. And the image is improper. Next one, between F prime and the lens. Just like before. Parallel light rays, focus towards the focal point. Light ray that passes through the center of the lens goes through unrefracted. Note that those two light rays are diverging. And then you can also do for the focal point, right? Focal point F prime, the light ray that passes through that extends through the focal point F prime, right? In reality, the light ray is going in this direction, so you have to extend it toward the focal point. So it is refracted parallel to the axis. Okay. Now the image is not formed behind the lens, the image is formed in front of the lens. And because it's formed in front of the lens, you get a virtual image. This image cannot be projected into a screen, on a screen. And the image becomes larger. It's a larger image that's magnified. It's not small, it's magnified, right? So then, okay, so those are the conditions that we have for a converging lens, right? Past F prime and before F prime. Okay, here you go. Like that. Let's take a look at our simulation. We go to simulation, we gotta get lenses. Lenses and mirror simulation. This is a mirror lab. Concave and convex lenses. Here you go. That's the one. Okay. So the focal point is 4 units. I want to make it closer. So you have, note that the smaller the focal distance, the thicker the lens is, right? You must refract more. In order to get the focal point closer, you gotta refract it more. He's using exactly the same light rays that I used, right? Parallel to the axis, through the center of the lens, and passing through the to the mirror image of the focal point, F prime. Okay, he's using exactly the same light rays. Okay, the further away the object is, the closer it gets to the focal point. That's what happens to the image of planets, the stars, the sun, the moon. The image is formed at the focal point. Now, as we get closer and closer to F prime, the image is formed further and further away from the focal point. Okay, let's go back here to 4. Here you go. Look here. This is a behavior similar to that of the mirror, right? If the object is located at distance 4 from the lens, the image is also going to be located at distance 4 from the lens. Okay, and past this point, the image becomes larger than the object. See that? Image here is 5.16, whereas the object here is 1, 2, 3, right? 3 units. At this point, the image is equal to that of the object. So here we go, as we get closer and closer to the focal point, the image grows larger and larger until we form a improper image. Here you go. Here's the light rays that are parallel to one another. No image, parallel light rays. At this point, we're going to form a virtual image. Okay? Look at the virtual. The behavior is very similar to that of the mirror. Okay, here you go. Here's the virtual image forming. Okay, but we cannot define a radius of curvature, even though you cannot define a radius of curvature, a single radius of curvature for the lens. The formation of the image at twice the focal distance behaves similarly to that of the mirror. Okay, so the same type of behavior for a mirror. Okay, positive lenses. Let's write that down. What makes a virtual image virtual? Okay, an image is virtual whenever you cannot project it onto the surface of a screen. Okay, that's the very definition of virtual image. Real images, you can project them over a screen, just like the image of your movie, right? In the movie, when you go to the movie theater, what do they have? They have this lens system there behind that's projecting the image of the film into a larger screen, right? That image that you see projected to the screen is a real image. A virtual image cannot be projected onto a screen. A virtual image for a lens, you're going to always see it not behind, but in the same position as the object. That's the important difference here. Okay, let's write it down. Here you go. Virtual images, virtual images cannot be projected onto the surface of a screen. Okay, cannot. Here you go. For mirrors, virtual images are located. Let's see, what exactly does that mean? Is it because the virtual image usually projects behind the object itself? No, no, that's not the point. No, that's not the. I'm going to write that down right now, Raymond. Hang there. For mirrors, okay, virtual images are located in the opposite side of the object. Okay, with respect to the mirror, right? So if you have an object in front of a mirror, the virtual image will always be behind the mirror. Okay, virtual images are located in the opposite side of the object. Let's see, we are located behind. Let's put it behind the mirror. Are located behind the mirror. Okay, or on the other side of the region where the object is located. Okay. Now, what about for lenses? For lenses, virtual images are located in front of the lens, or on the same side of the region where the object is located. Okay, that's very important. Cannot be projected. Okay? If you cannot project the image, then that image is virtual. So let me show you here the illustration, right? Now, here you go. Here is do you see here? Here's a virtual image. Notice that for the lens, the virtual image is on the same side as the object is with respect to the lens. For a mirror, the virtual image is behind the mirror. Do you remember that? Okay. Let me put them side by side so you can see, you can compare them better. Oh, it's not here. Should be in the other one. Let me get view here. Windows. Oh, that's a divergent mirror. Okay, that's what you see here is a real image. Okay, and that's a real image formed by the. Oh, it's too large. Okay. Okay, here you go. I'm gonna put it side by side. This is a virtual image formed by the mirror. And this is a virtual image formed by the lens, okay? Virtual image formed by a positive mirror, virtual image formed by a positive lens, okay? Note, see that the virtual image of formed by the mirror is behind the mirror, whereas the virtual image formed by the lens is on the same side, is in front of the lens. In front of the lens with respect to the object, right? That's the frontal part, that's the part that's behind. That's the comparison that we have. And then we can also have a comparison here for this one. Reflection. Okay, that's a real image. Let me see if it's if I don't want that, I want the other one that correlates. I want, here you go, I want this one here. Okay, I want this one here. Comparatively, that's a comparison here. Okay. Real image. Real image for a mirror. Real image. Let's see what's going on here. Oh yeah, the mirror is not very visible, right? The mirror is almost invisible because of this line. Okay, now we have it. We have a better drawing here. That's how you compare one to the other. And that's what we have for the, let's see if I have anything else I have to write there. Here you go. For mirrors, virtual images are located behind the mirror or on the other side of the region where the object is located. For lenses, virtual images are located in front of the lens or on the same side of the region where the object is located. You know, real image is all the way around. The real images can be projected onto the surface of a screen, onto the surface of a screen. For mirrors, real images are located in front of the mirror. In front of the mirror or on the same side of the region where the object is located. For lenses, real images are located behind the lens or on the opposite, on the other side of the region where the object is located. The behavior of images formed by thin lenses, not just any type of lens, but thin lenses, is similar to that of a mirror, because the equations are the same, right? Are the same. And then we get to the point where we can start talking about negative lenses. Okay, good. Okay, mirrored. Okay, here you go. That's the symbol of a negative lens. That's the symbol of a negative lens with those arrows inverted. Okay. So just like before, we go ahead and draw our light rays. Right? Light ray parallel, draw the lens, focal point F prime. In this case, the main focal point is going to be in front of the lens because the lens is negative. Okay, so those are diverging lenses. So any light ray parallel to the axis is going to diverge. And then you draw that, but it's going to diverge in that direction such that the extended region of the light ray passes through the focal point. Okay. Here is the light ray that goes through the mirror image of the focal point, which is F prime. Okay. That light ray that's pointing towards this F prime point is diverged parallel the axis of the lens, the principal axis of the lens. And then any light ray that goes through the center of the lens, it goes unrefracted. Where does the light that goes parallel to the axis go? Okay, no, it goes to infinity. Okay, it goes to infinity, right? So this, are you talking about this light ray or this one here? You must be referring to this one, right? The red. Okay, the red is refracted. All those light rays, they go towards infinity, okay? All those light rays, they go towards infinity. Let's see, this one, you know, propagate all the way down to infinity. This one propagates down to infinity. It stops at the negative lens. Let me see. This one, are you talking about this one here? Bend upwards. Okay, this one that bends upwards. Yeah, that's right. It goes upwards. It diverges, right? And again, this light ray goes to infinity. Okay. The smaller red one. Okay, the smaller. Okay, are you talking about this one here? So the smaller red one also follows the light ray from the focal point. Yeah, that's right. See the extension, the extended direction here? The light ray diverges, but it diverges in a proper direction, right? It diverges in a specific direction. The direction that it diverges is that away from the focal point. Oops. Away from the focal point. Okay. Okay, diverges away from the focal point. We can even see that in the simulation, right? And here goes. And now what do we do? The intersection of all those light rays is the point where the image is formed, right? So here we go. We have this light ray here that let's say this light ray here that is parallel to the axis. You got to extend backward. It crosses this backward dashed line. And it crosses also this other line here. That's where the image is formed. We can do that in the simulation as well. Here you go. See how, let's get this guy here. Okay, we gotta change it. Gotta change the focal point of this guy. Ah, okay, must be here. Let's see. Yeah, that's here. Okay, that's how you change the type of lens here in the simulation. Okay, you gotta move the focal point to a different point. So let's put it here. Now we have a divergent lens. Here's my object. Let's right, parallel, right, parallel to the axis. Towards the image of the focal point. Okay. Toward the image of the focal point is divergent parallel to the axis. Light rays parallel to the axis is that diverges away from the real focal point. And then passing through the center of the lens, it goes unrefracted. All those lines, whenever you extend them backwards, you get the point, find the point where the image is formed, right? This image is upright, virtual, right? And smaller. Let's move it, see that? You start to increase a little bit, but it's still smaller than the image of the object. It doesn't matter where the object is located. Okay? So that is just like the negative mirror too. Almost, the only thing that differs is the number of light rays and how the light rays are, and how do you project the light rays, okay? That's what changes here. Okay, so boy, that's basically what this chapter is all about. Converging lens, diverging lens, okay? Then there is this organization of the table. The image of the penguin. If you have played with lenses and mirrors, you can clearly see the image of the object, okay? So if this, the case of, let's say this penguin here in front of this positive lens, yeah, you do form an image of the penguin that looks just like the penguin, but upside down. It's really impressive, okay? That's how images are formed in a camera. In your regular camera, a lens that creates an image behind the lens, and you can really see this image. It's really neat. When I first saw for the first time, I couldn't believe it. That you can form an image like that by the lens. But we are talking about real images, right? Virtual images, you see them with your eye. You see that with your naked eye. Our image produced by a system of two steam lenses. And then we have systems of lenses, right? We're going to cover that as well. But now, any questions? Can an image ever be real and upright? If you're using just a single lens, no. Okay? If you're using just a single lens or a single mirror, no. But if you combine lens, yes. Okay? If you combine lens, yes, it's possible. There was even the case of, it's just like the image of the eye, right? The image that the eye forms in the retina. The image that the eye forms in the retina is upside down. Right now, everything that you look at around you is forming an upside down image in the back of your retina. However, you do not see objects upside down, right? Nobody see objects upside down. Okay, we don't see objects upside down because the brain processes the image and inverts it back. Okay, the brain does that. The brain is just like a computer that processes images, right? And then there is this case of people that they build eyeglasses to invert the image, right? To see the images inverted. Let's see if we can find that in the internet. It's a very interesting situation. One day I want to do that. I want to wear glasses that can make me see inverted images, right? Eyeglasses, lenses that invert images on the retina, right? Let's see. Upside down goggles, also known as invertoscopes, okay? Those things exist by Russian researchers, are optical instruments, upside down goggles, that's how they call it, that invert the image received by the retina upside down, okay? They're used to study human visual perception, particularly psychological process of building a visual image in the brain. So we have here you go, Wikipedia. Okay, upside down goggles, invertoscopes. So, and in fact, under normal circumstances, see here the eye of the guy is upside down, right? You can see his eye upside down. Under normal circumstances, an inverted image is formed. Under normal circumstances, right? An inverted image is formed on the retina of the eye. With the help of upside down goggles, the image on the retina of the observer's eye is turned back straight. And thus the space around the observer looks upside down. They even have patents, right? Look here, they even have patents on that. Upside down goggles can be used to demonstrate human adaptation to inverted vision and as a method of preventing motion sickness. That's what they claim. Recommended using upside down goggles for nausea adaptation for space travel. Okay. Hubert Dolzal, this guy here, 3. Living in a World Transformed, Department of Psychology, Northeastern Illinois University of Chicago. So I always want to wear those goggles one day, see how it looks like. And they even have patents. See that? They can also be used to train special. Let's take a look at the patents. Virtual archive. Where are the patents? I don't see the patent here. Patent here. Here you go. Notes. It's a Russian patent. See that? RU stands for Russia. So is there a second lens, or does the brain automatically flip things? Is there a second lens, or does the brain? We gotta study it carefully. I want to look into that. I believe it's just one lens. You don't need a second lens. Okay, I gotta remember how they do that, but there is a way to do that. Yeah, there is a way. It's a lens that you put in front of it. The lens is adjusted in such a way, has a focal distance, and so on, that makes the image in the retina upright. Okay, here you go. That's the patent. And there is also the US patent. Okay, this US patent is easy to find. Prismatic image transposing optical system. Let's take a look at this US patent. This one is easy to find. I'm not sure if the Russian patent is easy to find. I'm gonna go to Google Patents. Okay. US patent. An old patent, 5 million must be around okay, 1989. That's the patent here. A lightweight optical systems to enable a person where you such a system to transpose viewed images. The apparatus comprise removable, elongate the lighter than glass prism. Oh, they used the prism in this case. They didn't use a lens. Okay, yeah, they didn't use a lens. Here's the PDF document. Here's the okay. So it's a prism. You can look at the yeah, here you go. Here's the prism. Looks like that's the prism. So it's not a lens. The one for the lens should be the Russian patent. But I don't think we are going to find the Russian patent easily. Oh yeah, they do have it. Huh, interesting. Okay. Method of training of human spatial capabilities. Yep, they do have it here. I want to see the drawings. Okay, everything in Cyrillic, right? That's the Russian patent. And then they translate Google translated it to English. Let's see the drawings. I want to see the drawings. The drawings, I don't have to know Russian. Well, they don't have drawings here. What a shame. Yeah, they don't have drawings here for some reason. Huh. That's disappointing. But here's the translation of the whole patent. Okay. I have to look carefully, Raymond, what are the characteristics of the lens, but from what I remember, it's just a single lens that inverts the image in your eye. Okay. So it's 10:11. Let's see how we are doing here with the syllabus images. Okay, it's 10:11. Let's go for our break. Okay, 10:15. Let's see, 10:11, and I need to. I'd rather finish this thing today. Here you go. Break 10. Let's see, 12 a.m. to 10:27, right? So in 1 hour and 45 minutes, we are going to have our exam, and I will publish the exam there, and you will be able to see. You'll be able to see the exam there. Okay, it's prepared, and you don't have any questions. Any questions? So I see you in 15 minutes. I'm back here. So here in your book, we have the case of the inverted image goggle, right? What you see right here is exactly the case of the inverted image goggle. And let's take a look how it goes. We have an object, okay, and we have a lens, and then we have a second lens. So if you have this object this way, it forms an upside down image, right? And this upside down image can be reinverted by the second lens. And now we have this upright image here. So you have to use a set of lenses. Now, how does it apply to the upside down goggle, right? Well, that's simple. What you see right in here is going to be the lens of the eye. Okay, and what you have here is going to be the upside down, the lens of the upside down goggle. And then you have to have the right focal distance so it matches the focal distance of the eye. But basically that's the way we do it. Okay. So this is that would be this one here. This item A, right? Then you have different items. Okay. Here's the case of the first image in front of the lens, the first image on the back of the second lens. Okay, so that's how we find out an image formed by two lenses. First, you draw the image formed by the first lens and ignore the second lens. And then in the next step, you treat this image. In this case, the image is real. Okay, ignore the first lens because you already have this image, and this lens here is gonna image the final, is gonna create the final image, okay? This image behaves as an object, P2 is the distance of the object to the second lens. Here you go. P1 is the distance of the object to the first lens. It goes somewhat like that. I'm gonna do here in my PowerPoint slide. I'll copy this one here. I'm going to do right in here. Right, system of two lenses now, and then I'm gonna zoom out. I'm gonna make this axis longer. So I can fit everything there. View grid lines. This axis is not very horizontal, right? You go now. You can get it right. Good. Object, and I'm gonna put another lens here in this drawing. Let's say here. And then I'll call this one F1, F1 prime, right? Script. It should be F prime 1 looks better. Yeah. Which one? In the book or in my drawing here? The drawing? Oh, it's positive, right? See the arrow? The arrow is in the proper direction, so those are positive lenses. Negative lenses are like that, right? That's the drawing of a negative lens. Okay? So here you go, and second lens, and then I'm gonna draw it should be F1 prime, F1. Ooh. I don't need that. That's gonna be the F2 prime, and that's going to be F2. It can be different focal distances. Yeah, in general, it's gonna be different focal distances. This is just for you to have an idea how we do those upside down goggles, right? I'm going to erase this one here. I'm going to call that L1, right? Lens 1. And that's going to be L2. And one of the light rays is parallel to the axis, right? And then it converges towards the focal point. Object lenses, lens 1, lens 2, light ray parallel to the focal point, to the principal axis, right? And converge towards this one that I want to copy. This one I want to copy. I don't need that. I don't need this one. Good. And then we're going to need another light ray. And I'm going to draw it. It's a different color so you can distinguish. I'm going to make it black. And then okay, and then we form an upside down image right in here. And that's what the book calls image 1. I'm going to dash it. No, that's not, no, not good, not good. Yeah, it looks like I'll have to just make it gray, right? And now I can go ahead and form the image that the second lens is going to form and work out on the image that the second lens is going to form, right? I'm going to put it, let's see, a different color as well. Red, let's put this color. A little bit thicker to look nicer. Okay, and now we need another light ray. Here we go. One more light ray, and let's do it a different color. This light ray, I'm gonna make it green. Yeah, this image is gonna be very small because the object, this objects for two, right? Here's the object for one, and then that's the image of lens one. The image of lens one is the real object of lens two, okay? That's how it goes. And then we're gonna have another light ray. And finally, we form the image of, let's call this one object of one, right? I call this one object of one, capital O. And I'm gonna bold-face it as well. Bold-face, everything here is gonna be bold-faced. And now this one becomes image of one, which, by the way, is also the object of two. Okay, image of one, capital I1, which, by the way, coincides with the object of two. And by the way, because the image is in front of the lens, the object of two is going to be a real object. And finally, two lenses, right ray parallel to the axis, converge towards the focal point of one, second light ray passes through the image of the focal point of one and is refracted parallel to the light ray. And then at this point in time, we form image of one. It still didn't become object of two, okay? It's going to become object of two in the next slide, right? We still, image of one. Okay. Well, now it's object of two as well. Light ray parallel to the axis, right? Converge towards the focal point. Light ray passing through this, the image of the focal point of two, and refracts parallel to the axis. And finally, we form the image of two. Which, by the way, is straight up. I'm gonna change this shape here. See if you've got this. No, not what I want. This one maybe. Yeah, let's use this one. You. Yeah, it's gonna be very small. What a shame. Okay. Yeah, very small, right? That's gonna be my image of two. And now the image is upright. you want to get it the proper way, you gotta play with the focal distance of this one with respect to the focal distance of this one here, right? You gotta know the focal distance of the eye. 1044. That's what we have for two lenses, a system of two lenses. There are other configurations, right, that you can use. The direction of the arrow I1 and I2 indicate how one will view the object. Okay, the direction here, the direction of the I1 indicates how, if this one here is the eye, right, the lens of the eye, the direction of I2 indicates what would be the direction of the object that you see, okay? Because the image is being projected upright in the eye, when the brain processes this image, you're going to see upside down, okay? I1 is just an image, a real image that's formed by the first lens, okay? The first image that's formed by the lens, by the first lens. The first image is upside down, right? And then, we did this whole exercise to figure out how we can build an upside down goggle, right? If the upside down goggle managed to project the image upright in the retina, then the brain is going to invert it upside down. That's what it's all about. Does it make sense, Sydney? Okay, good. And what I was told, although I haven't seen evidence for that yet, I was told that while you keep on using these upside down goggles, eventually the brain adapts to the upside down goggles and reinverts the image for you. Okay, so no matter, even if you're using the upside down goggles, eventually after some time, the brain process the image and then you start seeing upright all over again. Okay, that's what I was told. I do not know if it's true, but it makes sense. It makes sense, right? If the lens projects an upside down image in your retina and then the brain inverts the image upright, so there must be some advantage in seeing objects upright, right? There must be some evolutive advantages of seeing the object upright. There must be some evolutive advantages of having the brain to reprocess the image so you can see upright. So if you then start using the goggles to see everything upside down, most likely eventually the brain identifies that and reverse the image. Okay, and reverse the image. So the brain, imagine, right? What would be like living in a world that everything is upside down, right? Imagine that. The sky would be downstairs, instead of upright. But then you'd have the impression that you're walking on the sky. No, it doesn't make any sense, right? So there must be some evolutive advantage of having the brain doing that. Having the brain inverting the image. Okay, if you want to increase the size of this image, all you have to do is bring this lens closer to the other, okay? Let's do the other drawings just like we have. What I did here is this item A, okay? The image is in front of the second lens. Okay, so what if the image one is formed behind the second lens? That's what this is all about. That's what this illustration is all about, right? Oh, you're going to see a virtual image. The object is virtual and the image is going to end up being virtual as well. That's what this item B is all about. Okay. I2 is somewhere to the right of lens 2. Okay, and C. Let's see C here. Now the image I1 is between the focal point of the lens 2 and the lens 2. Okay. And here's the image that you see. You see a magnified image. Okay, because that's what, and the object here is also considered real. The object is considered real, right? What about this one? Now the penguin is between the focal point of 1 and the lens. Okay, and the image is going to be virtual. This virtual image is seen by the second lens as a real image. So you have this second image here. Notice that he's ignoring the second lens in the first step, right? And then you can also have a negative lens. A negative lens is going to produce a virtual image, right? This virtual image will behave as a real image for the second lens, which is going to produce a real object. This virtual image is going to behave like a real object for the second lens, and then it's going to produce a real image behind it. And then you have all the way around. What if swap, right? Positive and negative. Penguin is far away from the focal point, produces a real image. This real image acts as a real object for the second lens, which produces a virtual image. Okay, those are not in scale, right? Those are not in scale. Those are the different types of image that we can get. But I think that we should stop here and give you a little bit more of room for the exam, right? Want to do that? Take a little break, for the exam before you start the exam. And it's 10:52 right now. We're kind of in terms of the time-wise, it looks like we're in a good shape. Okay, I will need to finish images next time. Let's do this way, okay? So the exam is going to be at 12 noon. I didn't publish the exam yet, but I will publish it 15 minutes before we start, okay? So yeah, let's take a little break right now, eat something before the exam start, okay? I'm putting the exam at 11:59 a.m., 1 minute before 12 noon. So we have a little bit more of time, and then you go until 2 p.m., okay? Any
Professor,
questions?
yes, where would we find the exam exactly?
Yeah, it's gonna be there in Canvas. It's gonna be there in Canvas. You can see it right now because I didn't publish yet. So once I publish, you will be able to see it.
Okay, thank you. And we're allowed to use our book?
Yeah, open notes, open book, yeah.
Okay, just no help from anybody else.
Yeah, so 15 minutes before we start the exam, I will publish it, so everybody's gonna be able to see it. Okay, and then you can start at 11:59 a.m., okay? That's okay. Yes. Okay, so see you in 45 minutes, right? Roughly 45 minutes.